Hi, welcome to the live session 8 of the Points of Topology and Detail course. This is Shovi and working on Newscaster access.
Yes,
So,
visible.
before starting, okay, so am I clearly audible?
Yes,
Okay, thank you.
audible. Audible also.
Okay, thank you, Mustafa, for confirming. Before starting today's session, please let me know do you have any question or any doubt from previous session or any question. And then,
Actually, I have a question.
yeah, tell me.
A connected space,
Okay,
a connected metric space having more than one point
okay,
each uncountable.
okay, okay. So, okay. So, the process of the solving this problem is was as follows. Okay. So, suppose assume XD be a connected metric space. Mother, thank you, Mustafa, for asking the question because this question is quite tricky also. Since you asked, so let me solve it, and that will help for other students also. One minute. Okay. So, suppose XD, X or D were connected metric space having more than one point. Okay. So we need to show what? We need to show x is uncountable. How to do? Choose x not belongs to x. Okay. And define the function f from x to r by x goes to dx x naught. Okay. Now, uh, okay, now x goes to dx x naught. Okay. Now, f of x naught is equal to 0, of course. And since x naught belongs to x and x has more than one point, so there exists y naught such that of course d of x naught y naught is non-zero. Correct. I mean it is greater than zero. Right. So this tells that f of y naught is greater than zero. So this implies what? This implies of image of f has at least 2 points. Okay, correct. And also since as if continuous, so image if is connected subspace of R. Okay. So either image if singleton or image if is interval. Now image if singleton that is not possible because image if contains at least two elements. So this implies what? Image if is an interval. And this implies what? Image if is uncountable because interval is uncountable. This implies what? This implies x is uncountable. Why? Because if x is not uncountable, if x is countable, then f of x has to be countable. So that is a contradiction, which says that image is uncountable plus x is uncountable. Okay. So that is the argument. Is it clear to you, Mustaq?
Yes, yes.
Any more questions?
I have another question.
Okay, Mustaq.
Are R and R2
Okay. R and
and
R2.
R2 are homeomorphic or not?
Okay. Okay. So, firstly, there are many ways. First of all, they are not. Okay. First of all, they are not homogeneous. Okay. But but and there are many ways to. But here we are going to discuss about the we are going to discuss argument, with respect to the connectedness things. Okay. So suppose this is real line. Okay, and this is R. Okay. So this is R and this is R. Okay. Suppose they're homeomorphic. Let if A part to becomes homeomorphic. Okay. Or let R to do R. Okay. So this implies if we restrict F by R minus single point is also homeomorphic. But such a situation, but that is not possible. Why? Well, R2 minus a point is connected, but R minus a point is always disconnected. That is, here this point goes to here, and then omitting this point, R minus that point is connected, R minus that point, R2 minus this point disconnected. So this is disconnected, and that's so left side is disconnected, right side is connected. That's why. So that's a contradiction. Yeah. So that's a contradiction, right? So this tells that R2 and R are not. Well, I must say one thing that intuitively it is clear that they should not be homeomorphic. Why? Because R2 has dimension 2, but R has dimension 1. But one thing must mention is that one thing I must mention is that here dimension means we are talking about the dimension with respect to the linear algebra, right? But there is also some concept of dimension of space, that is topological dimension, smooth dimensions, etc. Okay. Anyway, with keeping all those definitions in mind, one can able to show that Rm and Rn are not homeo for all m not equal to n. Okay. So this is what one can show, but directly we are unable to, but directly we don't have the required tool to show that. Okay, the required tool for which the tool which is required in order to prove this is nothing called as algebraic topology. Okay, so this tool is not currently in your syllabus, so right now we're unable to prove this. Okay, maybe in next upcoming semester we may be able to, upcoming semester hopefully may be able to prove it, but right now we are unable to prove it. Okay, yeah. So yeah, so that is the argument. Is it clear to you and Mustaq?
Yes. Yes.
Okay, thank you, Mr. for the information. Okay, any more questions?
No, no, I am. No one.
Okay, thank you. Okay, there is one. Shumesh. Shumesh, do you have any more questions? Shumesh, do you have any more questions? Okay, thank you, Shumesh, for confirmation. Okay, so now let's go for today's problems. So, okay. So the first question is as follows. First question is that consider R omega with box topology. Okay. So consider R omega box topology. Show that it is discount. Think about it. So what is R omega? So R omega is nothing but the Cartesian product of R, infinite Cartesian product of R with box topology. Okay. Now you need to show that it is disconnected. So for that, what you need to prove? You need to find out that is the hint is find out a separation for R omega. Okay. Try to find out a separation for that. Okay. Think about it and let me know. So, are you able to solve it? Anybody? Anybody, are you able to solve it? Let me know. Okay. So, the argument goes as follows. Okay. Yeah, it's quite tricky to understand, but anyway, so this is it. I cannot do anything for that. So, argument is goes as follows. Okay. So, we can write R omega as A union B, where this A consists of all bounded sequence of real numbers. This B consists of all unbounded sequence of real numbers. Okay. This consists of all unbounded sequence of real numbers. Okay. So, so R equal to A union B and each of these, so each of these are open in R omega. Why? Why? Because if we take A belongs to A, you can put U is equal to A1 minus 1, A1 plus 1 plus A2 minus 1, A2 plus 1. Then so the and so clearly that clearly uh, this entirely consists of bounded sequence. If A is bounded and of unbounded sequence if A is unbounded. Okay. So this still sorry. So this implies that R with omega has a separation. So this tells that R with omega with box topology is distinct. Okay. So this is the full argument. Are you able to understand? So let me one. So let me repeat it down. Okay. What? Okay. So here what we need to show our omega is with box topology is disconnected with the box topology, okay, not the usual product topology, okay. So in order to do this, we need to do what we need to write our omega is equal to a union b, where a and b should be set of open sets, okay. Now we are putting capital A to be the bounded sequence and capital B to unbounded sequence, okay. Now we're talking A inside A. Then putting U is equal to A1 minus 1, A1 plus 1, A2 minus 1, A2 plus 1, dot, dot. This contains entirely a bounded sequence of A is bounded and unbounded sequence of A is bounded. So this tells the R omega has a separation. And so this tells R omega the box topology is disconnected. So this is the argument. Okay. So are you able to understand? Please let me know. Please go through the argument once. If you have doubt, please let me know. Okay. So, so I hope that this argument is clear to everybody. So now let's go to the next question, namely that, okay, namely the following question. Show that the unity sphere Sn minus 1 in Rn is connected. What is the unity sphere? This consists of point x inside Rn such that norm x is equal to 1. We need to show that this unit sphere is connected. Okay. So, of course, directly it is not possible to show. Directly, what we can show? We can only show that Rn is connected. Sorry, Rn minus 1 is connected. That is one we can show directly. Directly, we cannot show Sn is connected. So, for that, we need to somehow use the fact that hint is that uh, make a continuous function, make a continuous function whose image is Sn minus 1. Of course, you need to make the continuous function Rn minus 1 decimal. That's quite obvious. That's why I'm mentioning. But somehow try to make some continuous function if the image is Sn minus 1. Okay, try to find out such a function. Okay, take your time, think about it. I shall be back in a few minutes. So that is make some f from something to Sn minus 1, which is also sub of something. Try to find such a function, okay? And also it has to be continuous, okay? Think about it as a back of a few minutes. Okay, so uh, I understand that is quite tricky also. So let me write the solution for you. Okay, so okay, so what you will do from where you are going to define the function. So define a from what to where are n minus 0 to Sn minus 1. X going to x by non x. Okay, first of all, observe f is continuous. Okay, secondly, observe f is surjective. Thirdly, our n minus singleton 0 is connected. So this implies Sn minus 1, which is nothing but f of Rn minus 0 is connected. So that is, so this tells that is Sn minus 1 is connected. Okay, so this is what we are trying to prove. Understand? So what we have done? Basically, we have done nothing. Hmm. So basically, what we have done, we construct a function f from from Rn minus 0 to s of n minus 1 by x goes to x by normal. And we check three things. Firstly, that f is continuous. Secondly, f is surjective. Thirdly, Rn minus 0 is connected. So this all together implies that Sn minus 1 is connected. Okay, so this is the argument. So basically, we have to construct a function f whose image is Sn minus 1 and domain is connected and f is continuous. So this all together tells that Sn minus 1 is connected since the continuous image of connected space is connected. Okay, so that is the argument. Do you understand? Uh, I have so. Please go through the argument once and let me know do you have any question or doubt. Okay, please let me know the argument once and let me know do you have any question or doubt. Okay, do let me know, is this argument clear to everybody? Oh, thank you, Shumesh, for your confirmation. So now, let's go for the next problem. Namely, okay, so there is a next question, namely, sorry, uh, find or construct an example. Construct a space which is connected. Find or construct a space which is connected but not path connected. Find or construct a space which is connected but not path connected. I must mention one thing. In general, path connected implies connected. Okay. But converse is not true in general. So try to find or try to figure out a space which is connected but not path connected. Okay. So this is quite tricky. Okay. So take your time. So such an example is quite difficult, quite tricky to construct also. Take your time and okay. So we also so let's not put that example making. So so I shall tell you that space, but you need to show that it's connected but not path connected. Okay. Put s equal to x comma sine 1 by x 0 less than x less than equal to 1. So that s closure connected but not path connected. Okay. Take your time, think about it. You need to show that the closure of the given set S is connected, but it is not path connected. Okay. Think about it and let me know. Take your time. Okay. So are you able to figure out that why is closure connected but it is connected but not path connected? Anybody? Anybody? Okay. So in that case, let me write down the solution. Okay. For that, let me check everything working fine. Okay, okay, okay. So let me write the solution argument for you. Okay. Okay. So first of all, first of all, is connected since it is graph of x goes to sine 1 by x. Okay. So and 0 less than x is equal to 1. So S is homeomorphic to open 0 close to no. So is connected. This implies S closure also connected. Okay. So this tells that S closure connected. So this is now done. Now we need to show S closure is not path connected. This is what we are going to show. Correct. Oh, so for that, what we are going to show is the following, or the trick is the following. By the way, so let me write down the graph of S, how it looks like. Okay. Now, so this is the graph of sine 1 by S. Okay. So S closure equal to S union um, S union 0 cross minus 1 plus 1. Okay. This is S closure. This line also inside S closure. Okay? Now let S closure path connected. Suppose we are assuming S closure path connected. So this implies direct step path F AC to S closure starts at origin and ending at a point of S. Then the set of those T for which f of T belongs to 0 cross minus 1 comma 1 is closed. So It has the largest element B. Okay. Then if B to C to S closure is a path that maps the point B into the vertical interval 0, comma minus 1 plus 1 and maps other points of BC to the points of S. Okay. So this tells what? So now, so put or replace BC, replace this BC interval by 0, comma 1. Okay. And let f of t is equal to xt, comma yt. So, 1 minute. Now put x. Now put a b comma c by 0, comma 1. We can put f of t is equal to x to y2. So then x0 equal to 0, but while x2 greater than 0, yt is equal to sine 1 by xt for t greater than 0. We show there exists a sequence of points Tn converging to 0 such that ytn is equal to minus 1 to the power n. Then the sequence yn converge. Contradicting continuity of f. Now to find Tn, we proceed as follows. Given n, choose u with 0 less than u less than 1 by such that Sine 1 by minus 1. Then use the intermediate value theorem to find Tn with 0 less than Tn less than 1 by n such that x comma Tn is equal to u. So that's the argument. So let me explain the argument in detail once more. Let me have some drink. Let me have some water first. So the argument goes as follows. Okay, so let me write the argument. Let me actually explain the argument for you. Okay, so um, 1 minute. Hmm. So in general, path connected implies connected. Okay, but the converse is not true. So the target was to construct or find a space which is connected but not path connected. Okay, well, constructing such a space is difficulty. So that's why I first gave you the space and asked you to prove that given space is connected but not path connected. Okay, and this space its closure is known as topological sine curve. Is known as topologist sine curve. Okay. So S is connected. Firstly, that S is basically the graph of x goes to sine 1 by x. Sorry, 1. X goes to sine 1 by x. So S is homeomorphic to open 0 close to 1. So this tells that S closure is connected. Okay. Now we are going to show that S closure is not path connected. Okay. For that, what we're doing? So firstly, this is the graph of the sine 1 by x. So there is nothing to explain actually. First of all, observe that S closure is equal to S union this vertical line. Okay, this vertical line is that also this minus 0, 1. Okay, now so this implies what? This implies that there exists a path f from a comma c to s closure. Okay, and which starts at the origin and ending at a point of s. Okay, then the set of those t for which f of t belongs to 0 comma minus 1 comma n is closed. It's obvious. So this tells that it has the largest element, call it B. Now, so then BC to S closure is the path that maps B into the vertical interval 0, minus 1, 1 maps other points of B, C to the points of S. Okay. Now put B, C and replace it by 0, 1. Okay. And let f of t is equal to x t greater than x0 is equal to 0, while x of t is greater than 0, and y t is equal to sine 1 by xt, while t is greater than 0. This so we show that now we are going to show that there exists a sequence of point tn greater than 0, so the y of tn is equal to minus 1 to the power n. Okay, so this tells that y of n does not converge contrary to the continuity of f. So to find a tn, we proceed as follows. Given u with 0 less than u less than x, 1 minus as the sign 1 by u is equal to minus 1, then we use the intermediate value theorem to find tn such that x of tn is equal to u. So that is the full argument. Please go through the argument once again. Let me know if you have any doubt or any question. Okay, please take your time and let me know if you have any doubt or any question. In case you are unable to understand, please let me know. I shall re-explain the argument. Okay, let's go through the argument once again. So, yeah. So kindly let me know, is this argument clear to you? Please let me know. Okay, Shumesh. Okay, so let me repeat the arguments. The argument goes as follows. Okay. So, hmm, so okay. Hmm. So put S is equal to. So first target was to show that its closure is connected. Okay. Because why? Because S is connected since it's a graph of a function. So that will be homeomorphic S will be homeomorphic to open zero closed one. So this tells that S closure is also connected. Okay. So there is till now there is nothing complicated. Okay. Now what we are going to show? We are going to show that S closure is also path connected. Okay. Sorry, we are going to show that S closure is not path connected. Okay. So for that, the process follows. First of all, the S closure is equal to S union this vertical portion. Okay. Now, suppose we are assuming that huh, suppose we are assuming that S closure is path connected. Okay. So this tells that there is the path F AC to S closure, start at origin ending at a point of S. The set of all those t for which f of t belongs to 0, comma minus 1, comma 1 is closed. So it has the largest element B. Okay. Then this tells that if BC to S closure is a path that maps B into the vertical interval 0, comma minus 1, comma 1 and maps the other points of B, comma C to the points of S. Okay. Now we are putting B, comma C and replace it by 0, comma 1. Okay. And now we are putting f of t is equal to xt, comma yt, then x0 is equal to 0. And while x of t is greater than 0 and y of t is equal to sine of 1 by xt is greater than 0. So we now going to show that there exists a sequence of point tn greater than 0 such that y of tn is equal to minus 1 to the power and then yn does not converge and contradicts the continuity of f. Okay. So for in order to find tn, what was the process? The process is to use the mean value theorem. So given n, we are choosing u such as 0 less than u less than x of 1 by n, such that sine 1 by n is equal to minus 1 to the power n. And the intermediate value theorems give some tn such that x of tn is equal to u. Okay. So this is a full argument. I mean, look, I understand that apparently this argument looks quite complicated, but believe me, this is not complicated at all. If you sit and write down the solution, you immediately with the argument what I have explained. Okay, so there is nothing really very much complicated. Okay, okay. So now Okay. So now let's go to the next problem. Mm, okay. Okay. So now let's solve a question. Question is, oh shit. The question is that let f S1 to R be a continuous. Show that there exists a point x S1 such that f of x is equal to f of minus x. So how you will do it? Think about it. That is, there exists a point which says that the point and its antipodal point minus x will go to the same place. How you can do it? Think about it. It is a only application continuity. So try to figure out how to approach this problem. Okay, take your time.
কে পাঠায়, সেই হোয়াটসঅ্যাপ চ্যাটটা কিন্তু ফেকও হতে পারে। মানে ফেক হোয়াটসঅ্যাপ চ্যাট কিন্তু বানানোও যায়। কিন্তু এটা বানানো যায় কিভাবে জানতে গেলে কিন্তু ভিডিওটা শেষ পর্যন্ত দেখুন, আর প্রসেসটা একদম সেভ করে নিন। দেখুন, এই জন্য শুরুতেই চলে আসতে হবে আপনার ফোনের গুগলে। গুগলটা ওপেন করে নিলাম। ওপেন করে নেওয়ার পর এখানে আপনাকে লিখতে হবে ফেক ডিটেলস জেনারেটর। এই যে লিখে নিয়ে এখানে ক্লিক করে দিতে হবে। ক্লিক করে দেওয়ার পর দেখুন এরকম একটা ওয়েবসাইট কিন্তু আসবে, ফেক ডিটেলস জেনারেটর। আপনাকে এখানে ক্লিক করে নিতে হবে। এবার ক্লিক করে নেওয়ার পর এরকম একটা পেজ খুলবে। এবার উপরে যে তিনটে লাইন আছে আপনাকে এখানে ক্লিক করে নিতে হবে। ক্লিক করে নেওয়ার পর কিন্তু এরকম একটা পেজ খুলবে, যেখানে দেখুন আছে সোশ্যাল মিডিয়া। আপনাকে এখানে ক্লিক করতে হবে। এবার এখানে ক্লিক করে নেওয়ার পর দেখুন এখানে আছে হোয়াটসঅ্যাপ চ্যাট। আপনাকে এখানে ক্লিক করতে হবে। এবার ক্লিক করে নেওয়ার পরেই কিন্তু এরকম একটা পেজ আসবে, যেখানে দেখুন একটা কিন্তু ডেমো হোয়াটসঅ্যাপ চ্যাট লেখা আছে। এইখানে কিন্তু আপনি সমস্ত কিছু এডিট করতে পারবেন নিজের মতন করে। দেখুন এখানে নাম আছে জন, পাশে এডিট বটন আছে। এখানে ক্লিক করে কিন্তু আমি আমার নাম লিখে দিতে পারবো। আমি সম্রাট লিখে দিলাম। अरे जल्दी से पैसे दो। पैसे नहीं है मेरे पास। पैसे नहीं तो मैं क्या करूं? मेरे घर में 3 दिन से कुछ नहीं खाया है, ले जाने दीजिए। अरे तो 3 दिन से नहीं खाया तो मैंने क्या किया? हस्बैंड को रखा क्या? हाँ? लाओ लाओ दे दो वापस। अरे जल्दी दो, इतना टाइम नहीं है। अरे अरे जल्दी भाग के खाना लेके देखो। लाओ भाग के।
Okay, are you able to solve this problem? Are you able to solve this problem? Okay. So let me write the let me give the argument for you. Okay. So so define G from S1 to R, x going to f of x minus f of minus x. Okay. Now this implies that g of x into g of minus x equal to f of x minus f of minus x into f of minus x minus f of x is equal to minus of f of x minus f of minus x at whole, which is always less than 0. So this that is g of x into g of minus x less than 0. So that is gx and g of minus x are of opposite signs. So this tells what? This tells that by mean value theorem, there x naught belongs to S1 such that g of x not equal to, which is equivalent to saying that f of x naught equal to f of minus x naught. Okay, so that is the argument. Is that clear to everybody? So basically, what we have done. So basically, I have not done anything extra. Only so if is a f1 to continuous function and g is s1 to r. So x belongs to f of x minus f of minus. Okay. Now gx into g of minus x will f. So gx into g of x is less than 0. Okay. So this tells that g of x and g of x and g of minus x, these two things are of opposite sign. So the mean value theorem tells that we have some x naught. This one says g of x not equal to 0 and f of x equal to f of minus x. So that is the argument. Okay. So there is nothing to. So there is so okay. So main thing is the mean value theorem, and the main trick is that you need to construct such a function quite wisely. So that is the main trick. Okay. So there is nothing thing no more. There is nothing more to explain. And the second thing is that you need to use that mean value theorem, which is of course everybody knows. So there is nothing to explain here. Okay. Okay. So go through the argument once again and let me know do you have any question or any doubt. In the meantime, let me find the next question for you. Okay. Shit. But yes, sir. Okay. Okay. So, okay. So I hope this argument is clear to everybody. So now let's go for the next question, namely, let f(x to x) be continuous. Show that if x equal to 0 comma 1, then there exists x such that f of x equal to x. Okay. And next part is what will happen. What happens if x equal to 0 comma 1 or 0 comma 1. Okay. So, so look. So as a previous problem, there also you need to find some function f of x equal to x. Okay. So here what we'll do. So I mean, look. So this tells what graphically this is obvious. Why? Because so sorry. So this is 0 comma 1. Okay. So this is 0 comma 1, and this is f of x. Now this tells that the function, whatever the graph f will be, it has to intersect this line at least once. Okay. So how to solve it? Think about it. Here also you need to connect. So basically, okay, first think about how to solve. Or basically, so try. So basically, the hint is the following. Hint is try to use mean value theorem. Okay. So somehow try to use mean value theorem on where? On some suitable function. On some suitable function. Take your time, think about it. What function or where we can make the mean value theorem work. Okay. Think about it, take your time. Okay. So the argument goes as follows. Okay. So put uh, okay. Suppose let okay let f0 is equal to 0 or f1 is equal to 1. Then done. Suppose not. Then put g of x is equal to f of x minus x. G0 is equal to f of 0 minus 0 is equal to f of 0, which is greater than 0, as f of 0 is not equal to 0, and g of 1 is equal to f of 1 minus 1, which is less than 0, as f of 1 is not equal to 1. So this implies that g0 into g of 1 are of opposite sign, are of opposite sign. This tells that there exists x naught belongs to 0 comma 1, such that g of x naught equal to 0. That implies f of x naught equal to x naught. So this is what we are going to show proof, right? Okay. So g of x equal f of x equal to x. Okay. Now either f of 1 is f of 0 equal to 0 of f1 equal to 1. So this tells us g of 0 is equal to f of 0. So this tells us g of 0 is equal to f of 0 minus 0, which is f of 0 is greater than 0. And g of 1 is equal to f of minus 0 is less than. So this tells the mean value theorem. So this is basically by mean value theorem. By mean value theorem. Okay, so this is one whenever x is 0, 1. But the thing is that such a thing is not true whenever x is. But for second part, if x equal to 0, 1 or open 0 close to 1, then such a thing is not possible. That is so keep put f of x equal to x by 2 half. This function f has no fixed point. Okay, so this is the argument. So now I have a question. So next question is the following. Okay, before going to the question, first thing, please go through the argument. Let me write down the next question also. Let. Okay, so I have the previous argument is clear. So for this next question, A is a subset of R2, and you need to show that R2 minus A is path connected, A is a countable. Okay, so I'm just giving the rough idea of this argument. So this R2, okay, path connector means what? You need to show there exists a path where you need to point. So I mean, look, so choose any two paths. Okay, choose any two paths. You need to show there is a path. Now, between any two points, there always exist infinitely many paths, right? This is basically uncountably many, but A is countable. So there exists at least one path which avoids A. So that is the between that is the main thing is there exist uncountably many paths between them. So that is the fact. Okay. So this is the argument. Please think about it and sit and write an argument. You will understand there is nothing to explain more actually. So yeah, so that's all for today. If you have any doubt or any question, you can ask me, or else you can ask it to an email, or else you can ask next live session. I shall give the reply as soon as possible. Yeah, okay. So we shall meet on the next Friday. That will be ninth session. Okay. Okay. Thanks all. I am leaving the session.